Welcome to Spring LIB.
Hello everyone, today we're doing problem 36 of chapter 11. And this question asks us, what are the products formed when we treat one hexyne with the following reagent? So we have a bunch of reagents here and we have our starting material, one hexyne. So let me draw that out. So hex means it's 6 carbons. So 1, 2, 3, 4, 5, 6. 1 means that's the position of the triple bond. So it's going to be on carbon 1. So let's do A. 2 equivalents of HCl. So we know from past examples that the alkyne can act as a nucleophile, and using one of those two electrons on one of these pi bonds, it can use that to nucleophilically attack possible electrophiles. So we know that when we have an HX or some sort of H halide, such as this, we know that we'll get Markovnikov's additions. Remember, the rich get richer. What does that mean? That means a side with more protons, so this carbon right here, will pick up the extra proton. So the rich will get richer. And remember, the reason for this is that by now picking up that extra proton, this proton here, we now form a secondary carbocation that's more stable than a primary carbocation if the proton were to be added on the other side. So now that we have a secondary carbocation, we also know that we have now our chlorine ion. Remember, when you make a bond, you break a bond. So this sigma bond between the HCl will break, forming our chloride ion. So we know that now chloride having extra electrons, being electron rich, it can nucleophilically attack the carbocation to neutralize it. And now we have one equivalent of HCl consumed, but now we have to add the second equivalent. So once again, we can do Markovnikov's addition because we still have those pi bond electrons. And if you can see here, the lower side has 2 protons while the upper side has 0 protons. So the side with more protons will get more rich with protons. So it's going to make a bond with that proton. When you make a bond, you break a bond. And then once again, I'm sure you guys can see this already, but now I'm going to get another carbocation intermediate. This side has now 3 protons. And now we have our Cl minus, which can act as a nucleophile once again to neutralize that carbocation. And this gives us our final product here. Now B is asking us to do the same thing, the HX. So remember, this can be generalized for any H halide. So HX, X being a halide. So this, with 2 equivalents, you see after 1 equivalent, we get this product, the alkene product. After 2 equivalents, we get the fully reduced alkane product. So you can imagine with 2 equivalents of HBr, we get the exactly same type of mechanism going on, but now the Cl's, the chlorines, will be replaced for bromines. So that's B. C. Now we have diatomic halide. So let's see how it looks like when we have a diatomic halide addition across the alkyne, sorry. So I'll draw my triple bond. So that's 1, 2 carbons, 3, 4, 5, 6. And we have Cl2. So I can redraw Cl2 as ClCl to diatomic halide. And once again, these are good leaving groups, and when we know something's a good leaving group, it's most likely going to be our electrophile because it has a potential leaving group. So now we have to identify the nucleophile. Nucleophile being, once again, the alkyne pi bond because of its electron-rich nature and its susceptibility to be used for nucleophilic attack. So once again, going through the least substituted carbon, Markovnikov's rule, the rich get richer, we'll make a bond and break a bond. So the whole idea of following Markovnikov's rule is so that we generate a more stabilized, a secondary carbocation instead of a primary carbocation. So secondary carbocation will be lower in energy and more stable. So now you can see that on this side, we have the chlorine that we just got added. And on this side, we have a chloride ion with a carbocation. That carbocation can be neutralized with the attack from the chloride ion. And now, as you guys can see here, we have trans addition across the alkene. But now we have another equivalent. We have two equivalents of Cl2. So we have another equivalent of ClCl. So the same thing is just going to be repeated. We'll go through one of the carbon nuclei, the least substituted nuclei, making a bond. When you make a bond, you break a bond. And now we just added that extra chlorine on the bottom side right here. Now we have a tertiary carbocation up here, the chloride anion, which can act as a nucleophile to neutralize this carbocation. And this will give us our tetra substituted halide. Just like that. So D is asking to what happens when we have water and some sort of acid with mercury. So let's draw that on the other page. So I'll just open up a new page. So we're starting with 1, 2, 3, 4, 5, 6, and we're going to have water and acid. So remember, any strong acid, so like H2SO4, I like rewriting this to HA, any strong acid. So now we can imagine that once again, we need to identify potential nucleophiles and potential electrophiles. So a potential nucleophile in this situation, well, we have these pi-1 electrons, and we can add, following Markovnikov's addition, we can make addition of some sort of proton on the more side with a proton, leaving carbocation intermediates here. So then we can add some sort of nucleophile thereafter. So remember, strong acids fully dissociate in solution to H plus and A minus. But this water, because it's an acidic condition, it actually exists in some sort of equilibrium with H3O plus. So because it's an acidic condition, so we actually have acidic water. So water will exist in an equilibrium with H3O plus. So we know that we'll pick up proton either from H3O plus or just from the H plus, making a bond. And if you picked up from H3O plus, then we would have to break a bond as well. Now we picked up that extra proton. We have now a secondary carbocation. And what do we have left? Well, we have A minus and H2O if we were to pick it up from H3O plus. Well, now we need to identify nucleophiles. So we know that oxygen, being electron rich, it can act as a potential nucleophile. So we'll use water. And the reason we use water, not A minus, well, water is the solvent. So for every 100 mils of water, we can assume that there's only going to be a few drops of acid. And even if it was a pure acidic solution, it's only, for example, 20% acid. So that means that for every 10 molecules of solvents, 8 of them would be water, 2 of them would be acid. So the likelihood of water attacking is far greater than A minus. So we know that water attacks, acting as the nucleophile. But now oxygen has 3 bonds. So we'll have a positive charge, but we still have that A minus. So A minus can pick up one of those protons because we have a positive charge and a negative charge. Plus 1 minus 1 equals 0. So why not just neutralize everything so it itself would truly be 0? So A minus will pick up one of those protons, giving those lone pair electrons to oxygen to form an alcohol and reform our acid catalyst. So next, what do we have? We have E, so hydroboration. So let's draw that. With some sort of oxidizing agent, so H2O2. So boron, we can imagine boron looks something like this. So we have 3 hydrogens, so we have 2 hydrogens on one side, and one hydrogen on the other side. So boron with 2 hydrogens is going to be larger and more sterically hindered than just this hydrogen. So we know that when you want to add boron, a little trick is, once again, identify your least crowded side. So side with more hydrogens. So the left side, the bottom side has more hydrogens than the right side. So we know that boron being larger, we'll prefer to add on the less crowded side. So we can write boron like this. And you can imagine that the sigma bonds are going to be formed on this carbon with the B, and this carbon with the H, and then we're going to break apart this pi bond. We're going to break apart this pi bond when we form these 2 new bonds. So we can form the product of that. And we just pick up that extra hydrogen here. Now the second step is some sort of oxidizing agent. So this is something that we just have to remember because the mechanism of going through this is beyond the scope of this course or any introductory organic chemistry course. So when we have some sort of oxidizing agent with boron, we just know that that's going to fully oxidize to a carbonyl group. So we know that if a carbonyl group has 2 bonds, that means we know that one of these bonds have to be broken because this carbon already has 4 bonds. So if you're going to add another double bond here, one of these bonds have to break, but we don't want to change the actual nature of this molecule. We just need to move around electrons. So obviously one of these pi bond electrons is just going to break and form a new hydrogen bond over here. So this is something you just have to remember, that when you oxidize boron, you get a carbonyl group, in this case an aldehyde, and then that pi bond breaks, giving rise to an extra proton adjacent to it. So next we have, so we're just actually using sodium hydride, so I'll open actually a new page for that. One, two, three, four, five, six. Sodium hydride. So remember, sodium hydride dissociates Na plus and H minus. Sodium being a counter ion, just a spectator, doesn't really do anything. H minus being a hydride, it's very, very reactive, doesn't like having an extra electrons on it. So what it wants to do is pick up an extra proton somehow to form H2 gas, hydrogen gas, and it'll neutralize itself and therefore be happy. So when you look at some potential hydrogens that we can take out and form this hydrogen gas. So obviously, this proton is the most acidic proton on this molecule. What does that mean? That means that it's okay for this alkyne to lose this proton because the conjugate base, when this is going to be a carb anion with the extra electrons from this sigma bond, this conjugate base will be stabilized by the high S characteristics in this sp orbital right here. And this is also going to be an sp orbital. So we know that this is going to be significantly stabilized, more so than any CH bond present on the molecule. So we know that we're going to make a bond, you make a bond, you break a bond, those 2 electrons goes towards the carbon nucleus now, and we form a very, very, very reactive carbanion with its sodium counter ion present also. So next G, we're also using a strong base, so you can imagine this amide is going to act as similar to hydride, so H minus and NH2 minus acts similar, so they're going to just rip apart your proton. But now we're actually adding some sort of electrophile. So you can see we formed a carbanion in the previous example, which is a very strong nucleophile. So a strong nucleophile will be very reactive to an electrophile. So we're going to add our strong hydrogen abstracting agent, or our base, you could call it. Then after that, we're going to add a strong nucleophile. So you can imagine, once again, that this nitrogen will pick up this proton, making a bond. You make a bond, you break a bond. Those 2 electrons on the sigma bond will go to the carbon nucleus, making our carb anion. Now we have a very reactive nucleophile, electron-rich carbon, doesn't like being an anionic ion. So we're going to attack through SN2 mechanism our electrophilic carbon, making a bond. When you make a bond, you kick off your best leaving group. In this case, it's a very good leaving group, being one of the halides. 1, 2, 1, 2. So we're good on carbons. And now, last but not least, we have this problem here. So once again, we're doing something similar here. So we're gonna rip off that proton, make a very strong carbanion nucleophile. We're adding an electrophile, but in this case, it's an epoxide. So we'll do an epoxide ring opening, and then remember when you hit your epoxide from the opposite side that the actual oxygen's on, you make a bond. So when you break a bond, those two electrons will go onto the carbon nucleus, making an O minus, and that's why we add water. So the water will protonate this, so it's going to be an OH remaining. So we know that everything's going to be neutral in our final product. So once again, we use this nitrogen to deprotonate our alkyne to form a carbanion, and then carbanion will now act as a nucleophile to hit our electrophile. In this case, epoxide. Remember, it's going to hit on the least sterically bulky side, but here this side, each side has 2 protons, so it doesn't really matter which side we attack on, they're equivalent. So we're just going to attack one of these carbons, making a bond. When you make a bond, you break a bond, so that electronegative carbon is happy to accept those 2 electrons. We have 1, 2, and we have an O minus, in which water can be used to protonate this electron-rich oxygen, making a bond. We make a bond, we break a bond, and then we form 2 alcohols. To form our final product. And is there any more? And that was the last one. So I hope this helps.